In section 2.5, we talked about transformations of functions, and I gave you a lot of examples on the graphing calculator in class. Basically, what's going to happen is if you start with any general function, for example, if you start with your basic run-of-the-mill quadratic equation, y equals x squared, and you add a number to it. For example, if I add 2 to it, I'm going to literally add 2 to all the outputs or y values of the function. So every ordered pair is going to move up 2 units. Oops, that one was in the wrong place. And that's what the function's going to look like. If I do something like this, y equals x squared minus 3, I'm going to subtract 3 from all the outputs of the original function. So I'm going to move everything down 3 units. And it looks like this. So the general rule for moving graphs up and down is if you have a function f of x, if you add a number to that function, it moves the graph up a units. And if you subtract a number from that function, it moves the graph down a units. Well, if we can move our graph up and down, we must be able to move it left and right as well. So let's go back to our general quadratic equation. 2, 3. There's my general y equals x squared. Let's say instead I want to look at y equals x minus 2 squared. If you plug that into your calculator, what you'll see happens is it takes all the inputs and it moves it 2 units to the right before it ever finds the output. So literally, this is what happens to the graph. And if I do y is equal to x plus 3 in parentheses squared, the plus 3 in parentheses is going to add 3 to all the original inputs, the x values, before it squares it. And if you do this one on your calculator, you'll find that it moves the graph 3 units to the left. So the general rule about moving graphs to the left and right is if you add a number to the input of the original function, you're going to move it to the left a units. And if you subtract a number from the input, you're going to move it to the right a units. Well, now let's talk about what happens when I do this. Let's go back to our original function, y equals x squared. And what if I say y equals negative x squared? And you plug that into your calculator. Well, what you're going to find is that that literally just flips the graph upside down. We say that it reflects the graph over the x-axis. And if you plug into your calculator this, something very interesting happens. Nothing happens. Matter of fact, it looks like the original graph of y equals x squared. And that's because if you remember, whenever you square something, it's a positive. It doesn't matter if you're squaring a positive or a negative. It's all going to come out positive. So it ends up looking like the original graph. It doesn't mean nothing happened. Something did happen. We say that it reflects over the y-axis. It's just that you didn't see anything happen. Now I claim that you can tell me what's happening to a graph without having to graph it. If I tell you that the original graph of a function is f of x equals x squared is called the parent graph. So if I want to know how the graph of x squared plus 3 is related to the original graph, I want you to notice the only difference is this plus 3. That plus 3 outside of the x squared moves the graph up 3. And if I want to know how the graph of h of x equals x squared minus 2 is related, I want you to notice that this minus 2 is the only thing that's different. It moves the graph down 2 units. Let's do this again, except for what we're going to change is going to look a little bit different. So we're still going to work with x squared. And I want you to notice in the next example, a, g of x equals x plus 4 in parentheses squared, there's a plus 4 in the parentheses. When that changes the input rather than the output, we're moving the graph to the left or the right. Well, if you see a plus 4, it moves it to the left, which is kind of the opposite of what you might think is going to happen. A lot of times we think when we see a plus sign, that must mean to the right, because to the right on the coordinate plane is the positive x direction, but it's actually the opposite of what you think. H of x equals x minus 2 squared. Well, that minus 2 in parentheses moves the graph to the right 2 units. What transformation has been done to the graph of f of x equals the square root of x to get g of x is equal to x minus 3, the square root of plus 4? Well, there were two things that were done here. We can do multiple transformations on a graph, not just one. This plus 4 on the outside, that moved the graph up 4. And this minus 3 under the radical, that moves it to the right 3. So the original graph, the parent graph of the square root of x, goes through 0, 0, 1, 1, 4, 2, 5, 6, 7, 8, 9, 3. That's the original graph. So when we move everything up 4 and to the right 3, I'm going to start with each of these dots on the graph. I'm going to go 1, 2, 3, 4 up, 1, 2, 3 to the right, put a dot. 1, 2, 3, 4 up, 1, 2, 3 to the right. 1, 2, 3, 4 up, 1, 2, 3 to the right. 1, 2, 3, 4 up, 1, 2, 3 to the right. And there would be the graph of g of x. Let's look at the square root of x again. We want to describe each transformation. Well, I had said that if you multiply the outside of the function, the outputs of the function, by negative, that reflects it over the x-axis. So what happens is if you start with this graph that goes through, I'll use green, 0, 0, 1, 1, 4, 2, 5, 6, 7, 8, 9, 3. When it reflects it over the x-axis, instead it's going to go down here. So there's the graph of negative square root of x. And then if you have the graph of the square root of negative x, when the negative is changing the input rather than the output, we're going to say that it reflects over the y-axis. What's that graph going to look like? Well, it's going to take that graph over here and instead do this. And I'm going to run out of space, but you get the idea of what it's doing. This is the square root of negative x. Now let's go back to y equals x squared here for a moment and talk about what happens when you multiply the output of a function by a number that's greater than 1. Literally what that 2 is going to do is it's going to multiply all the outputs by 2. So let's do this. This is at negative 2, 4. Well, the output's 4. The output's going to become 8. This output at this point here, which is negative 1, 1, is going to become negative 1, 4. 0 times 2 is 0, so it stays where it's at. 1, 1 is going to become 1, 4, and 2, 4 is going to become 2, 8. And, sorry, that doesn't look very good. There we go. And basically what multiplying by 2 did to the graph is it kind of made it skinny. We say that it stretched vertically. And functions will stretch vertically when you multiply them by a number bigger than 1. What if instead I had done y equals 1/2 x squared? Well, that would take each of the inputs and divide it in half. So this output here of 4, when you divide it in half, becomes 2. This output of 1 becomes 1/2. 0 divided by 2 is 0. 1 divided by 2 is 1/2. 4 divided by 2 is 2. And that's what happens to the graph. It widened. We say that it shrinks vertically. So when you multiply the output of a function by a number, and that number is between 0 and 1, it's going to shrink vertically. Let's describe all the transformations on the graph of f of x equals 1 minus 2 x minus 3 squared. Now, first of all, we have to know what the parent graph is, and the parent graph is x squared. What's happening to that parent graph? Well, it's getting moved to the right 3. It's getting moved up 1. Because the parentheses is being multiplied by -2, the negative is reflecting it over the x-axis. And the 2 is stretching vertically. So it's taking the original graph of y equals x squared, and it's first moving everything to the right 3, so I'll move everything to the right 3. And then it's moving everything up 1. It's then reflecting it over the x-axis. Nope. And then it's taking those and it's multiplying all the outputs by 2. And I'm going to run out of space, but in essence, this is what it's doing to the graph. So the orange graph would be the final graph. Let's look at a very generic graph now. We talked about what happens when you multiply the output of a function by a number greater than 1 or between 0 and 1. We need to talk about what's going to happen when we multiply the input by a number greater than 1 or a number between 0 and 1. So let's just call this graph f of x. And standard tick marks 1, 2, 3, 4, 5 on the x and y axis. What's going to happen if I multiply the input by 2? Well, I'm not really multiplying the input by 2. What I'm really doing is I'm taking all the x values and I'm multiplying it by 1 over 2. So, for example, this is at 0, 0, and 0 times 1/2 is 0, so that point doesn't move. This point's at 2, 2. The x-coordinate of 2 becomes 1, 2. This one here is at 4, 0. Well, it's going to move to 2, 0. 6, -2 is going to move to 3, -2. And 8, 0 is going to move to 4, 0. So this is what it does to the graph. We say that when you multiply the input by a number that's greater than 1, it's going to shrink horizontally by a factor of 1 over a. What if I want to do 1/2 x in my function? Well, that's going to take my x values and multiply it by its reciprocal, 2. So 0, 0 is 0, 0. But 2, 2 is going to become 4, 2. 4 0 is going to become 8 0. So the graph's going to kind of look like this. We say that it stretches the graph horizontally by a factor of 1 over a. So when you multiply by a number that's between 0 and 1, we say that it's going to stretch horizontally by a factor of 1 over a. The last thing that we want to talk about is even and odd functions. They're very important functions. They pop up all the time. An even function is a function whose largest exponent is not only even, but the graph is symmetric about the y-axis. What that means is if xy is on the graph, so must negative xy. That's what it means to be symmetric about the y-axis. An odd function is going to be one whose largest exponent is not only odd, but if xy is a point on the graph, so must be negative x, negative y, in order for it to be an odd function. Just because the largest exponent of a function is odd does not mean that it is an odd function. And just because the largest exponent of a function is even does not mean that it is an even function. You must check to see if symmetry exists about the y-axis or the origin. A lot of times you'll just be able to tell by looking at the graph, but sometimes you'll need to check the table to see if these conditions hold true.